Brett Lenz, PDC, it's good to have you back on the podcast.
Thanks, Steve. Good to be back. Thanks for the invitation.
Absolutely. It's always good to have somebody come back because they're kind of used to the format and we've had a discussion before. And I just think it sometimes can lead to a little bit more open conversation. So welcome back.
Yeah, absolutely.
Yeah. Real excited to talk about PEEK. PEEK is a high performance thermoplastic used in medical device, orthopedic, surgical robotics. And I'm interested to talk about that. And I was talking to a buddy of mine that's one of the lead engineers at a surgical robotics company. Mm-hmm. And I asked him about the use of PEEK for surgical robotics effectors and other surgical robotic components. And he said it's really picking up the use of PEEK as a replacement to metal because of its durability and strength and MRI compatible, right? So that's one of the reasons why they want to remove some of the metals for MRI compatibility. And also he said because of the strength and chemical resistance, it's in electrical properties, it's used as well in many of the components within the body because of its, especially if there's electrical circuitry, non-capacitive, non-conductive properties. So those are some of the points that he was telling me about the use in surgical robotics. And of course, we know about the use of PEEK in orthopedics and maybe even some neuromodulation applications. And so I'm excited to talk about PEEK. Let's get your thoughts on PEEK and how to maximize the properties of PEEK.
Yeah. So yeah, you're spot on. Everything you mentioned is very true. The really PEEK's a pretty amazing thermoplastic. It's highly temperature resistant. It's electrically non-conductive, so it's a good insulator. It's biocompatible, so it can be used in long-term implants. And it has pretty incredible mechanical strength compared to most other thermoplastics. Probably another knock-on benefit in the orthopedic space specifically is its modulus, so how it reacts to stresses, is actually pretty close to that of bone, of human bone. And so it's actually really advantageous in place of, say, instead of a titanium bone screw or something, it's going to go into, say, a hole in a bone. And as that bone stresses normally, the titanium, let's say, is way more rigid, way higher modulus. It's just going to sit there and kind of wallow out that hole a little bit over time. Whereas the PEEK will kind of breathe with it. It'll stretch and strain with the bone a lot more naturally. So yeah, it's a really, really cool material, wide variety of applications, anywhere where you need strength, where you need electrical insulation, where you need thermal insulation, where you need a long-term implantable that fits a lot of those bills as well. And you need something moldable. It's a wonder material.
Yeah.
Its drawbacks are it's a real pain to work with.
Yeah.
It's quite challenging to mold. There's a lot of nuance and a lot of kind of technical capabilities that are required to work with it. But that's something we've been doing for 20 years now and have a lot of expertise, and that's kind of what we're hoping to share a little bit today. You mentioned on kind of where do we enter into molding considerations and the parts that we get out of that. And one of the key ones I think we wanted to highlight today was talking about crystallinity.
Yes.
So PEEK is a semi-crystalline thermoplastic. So basically, as it cools, it forms some crystal structures in the kind of in the matrix or in the material, and that is key to actually achieving, particularly some of those strength properties.
Yes.
And that gets down to the processing. So, particularly in the cooling. So if you a lot of it boils down to if you cool the material too fast, you quench it. Basically, you don't give time for those crystal structures to form properly, and you can end up with a part that is weaker than it otherwise would be or should be, kind of by the book material specifications that you're after. A lot of other considerations that go into when you get into specific part geometries as well. that can affect that, like thin wall conditions and knit and things like that. They're all kind of very case specific. Um, but crystallinity is kind of necessary and an important aspect across all different parts and geometries.
And it's the degree of crystallinity, or the whether it's amorphous or crystalline, that kind of maximizes those properties that we're talking about.
Yeah, so to get into the plastics geekery a little bit, so PEEK is a semi-crystalline material. So it kind of has a mixture of traditional crystalline structure and um, the the amorphous kind of stringy,
Hmm.
like chaotic. It has a mixture of both. Um, the What you're trying to achieve is making sure you actually get the crystal side of that achieved in your part.
Right.
Um, the amorphous parts, um, basically, if you cool it too fast, it tends a little more towards that amorphous side of things, and it is more ductile in that
Yeah.
range. It's stretchier, but it's not as strong.
Yeah.
So you're looking for that hybrid of both of those that you get when you have a well processed part.
Okay. Yeah, I know. In the extrusion of peak, the process parameter that's most important to maximize crystallinity mechanical properties is the gap between the die head and the cooling bath. Basically, like you said, how quick you're quenching. If you're quenching too
Right.
soon, more amorphous, more ductile, but you're not
Right.
maximizing the properties. So maybe we can talk. This isn't a podcast about extrusion, but I wanted to give that. I'm
Sure.
an extrusion guy, so
Yeah. Yeah.
I thought I'd throw that in. But interested to learn about some of the approaches that you take in the mold design or approach, to really maximize the crystallinity. And also, you mentioned it's kind of difficult to work with. Some of the other characteristics you can kind of talk about related to outgassing and flash and shrinkage. If you can kind of go through some of those, that'd be awesome.
Yeah, absolutely. So I think, well, yeah, extrusion a little bit different space, but it's a lot of the same problems. And so
Hmm.
crystallinity is on the one, it's how you cool it, and probably to dive right into the mold design considerations that are there. Um, so PEEK is a high temperature material compared
Hmm.
to most thermoplastics. It's pretty high on the spectrum. Um, the That means it also has a relatively high transition temperature, or kind of uh, melting point, or point that you need to cool it to get it to freeze and solidify. Um, the That means your mold temperature for cooling is actually quite hot,
Hmm.
where a lot of other materials mold temperatures might be in the maybe anywhere from 50 degrees Fahrenheit to maybe 150 degrees Fahrenheit. Peak is up in the 350 to 400 degrees Fahrenheit as the cooling temperature for the resin, because the melt is up in the 800s.
Yeah. It's
Um,
hot. It's
is
hot.
very hot, yeah.
Yeah.
Which is one of its big challenges to work with. Is
Yeah.
just physically dealing with especially if you have parts with inserts or hand loads and things like that. You just have handling concerns with that. Um, the cooling of the molds themselves and maintaining that temperature in the molds gets a little non-conventional. In those more normal temperature ranges, the very, very common cooling method for most molds is to use pressurized water.
Hmm.
And you can use a thermolator to really accurately control that and get a really high flow rate through the cooling lines. So you have very little variance in it. Um, to get water up to 350 to 400 degrees F, you have to pressurize it. It will boil before it gets there, if you don't pressurize it and move up the PVT chart, basically. Um, that brings inherent risks if you were to have a line blow or something fail or whatnot. Now, that's both going be- coming off under pressure and then
Hmm.
creating steam immediately. So it's a bit of a safety hazard.
Hmm.
So a lot of places don't like to do that, including us, for that reason. Another option is oil, that can achieve those temperatures at lower pressures. We do exclusively medical molding in a Class 8 clean room, so that's kind of just a dirtier material that's bigger risk of contamination and things like that. So we avoid the oil. So we opt for electric heating, which has some drawbacks, but we've managed to come up with a really good kind of classic design approach that we very much standardized to work around those drawbacks. So we'll look at that in a minute. We'll take a look at one of our PEEK mold bases. A lot of other things at play there as well. When we have these high temperature materials, you've got a large temperature delta from your melt to your frozen part. Has I call it a mid-range shrinkage rate. Not as high as say like polypropylenes and things like that, or some TPUs. But it's certainly not the nice tight windows that you get with polycarbonates or acrylics and things like that. But it does have a decent shrinkage range you have to worry about, and variation that can come from that. Particularly, we're working on really small parts with really, really tight tolerances. So thin wall conditions, small gates, places where a little bit of shrinkage variation can have a outsized impact on the tolerancing. So we have to put a lot of work into doing mold flow analyses, simulations to kind of predict some of that stuff, decide if we need to add extra gates or move gates or thicken wall sections or redo geometry so that we're controlling where a knit line is going to land, things like that.
Yep.
With all of that, we also need to be really concerned about how we do venting in the tools from a couple different angles. So one, PEEK is a relatively gassy material. So while it's molten and it fills in, it creates a fair amount of off-gassing, and that gas needs to go somewhere. Similar to that, any mold cavity, if you close it up, you have air inside of that cavity. And kind of traditional molds just fill that and have vents in the mold that allow the plastic flow to push the air out through the vents. PEEK needs a little help with that, because the other contending challenge of PEEK is that it is quite easy flowing and will flow into very small crevices. So it's and result in flash. So anywhere you have a match line on a part, the main parting line between the two mold halves, anywhere you say maybe have a core pin or a side core feature or something like that, where there's a match line between two different pieces of steel, PEEK is very prone to trying to squeeze its way into those little crevices, which are the same little crevices that act as your vents. So you have this competing space for, I need my vents to be big enough to get all that gas and air out, but I need them to be not too big that I flash.
Yep.
And the window for that is about 2/10,000ths of an inch. It's not much, a few micron. So that's the challenge we're working with. One of the major things we do there is we employ vacuum venting on a lot of our tools. So we'll intentionally kind of behind those match lines, connect those match lines and those vents to a enlarging kind of set of plumbing, basically, and pull vacuum on that to empty the cavity of air as soon as the main mold halves close and effectively seal. We're then evacuating the cavity of all the air. And then while the shot is going in those few milliseconds, honestly, that the fill happens through, we're pulling any gas that's at the flow front out through those vents with vacuum assist.
Interesting.
So maybe without further ado, let's take a look at example mold base that shows a lot of this.
Excellent.
Yeah.
So tell us what we got here.
Yeah. So we're looking at a cross-section view, kind of right through the middle of a PEEK mold base that makes a very small little cylindrical part here. Pretty simple, just a cylinder and a hole through the middle. It's set up in what are called clapper slides. So we're looking at one of two mating slides. There's another one on the other half here that just mirrors of each other that come together to form the two halves of this. And it's got a set of these two opposing core pins that form the inside diameters there. So maybe starting big and then narrowing down small.
Mhm.
Um, our main mold halves here. So these 3 plates here are the what we'd call the A half of the tool, the stationary half that's bolted on to one half of the platen. The
Mhm.
mold will then, when it opens, separate right here through this plane, and then everything south of here is the moving or the B half of the tool,
Gotcha.
including the slides themselves. So the part, when we open up, part stays on the slides on the B half of the tool. These core pins here pull away from the part, um, and then the slides open up, and this entire plate here is connected to the ejector system, which lifts the part off of these core pins. So that's kind of the main mechanism of the tool. If
Okay.
you're a molding nerd out there, there you go. What's really special that we're doing here, that we can point out, is coming back to that cooling and to that vacuum venting. Um, how we do the cooling in these, we mentioned we do electric heating
Yep.
for the cooling for the plastic in this. Um, our goal is to get a really consistent temperature right around the part cavity. That's what matters.
Yep.
We want the part to um, cool in a controlled manner. The best way to do that is to just try to hold this tool steel that's touching the part cavity. So all of these surfaces, we want to hold those at as constant a temperature as possible.
Mhm.
Um, in traditional lower temperature molds, you'd do that by bringing water lines in, and you'd get them close, not too close, but close as you to the cavities. Um, the too close being you don't want to make hot or cold spots. You don't want it so close that you kind of see the gradient because you're so close to the source of the cooling.
Mhm.
So that's the idea we're trying to spread here. And what we do with this electric heating, the kind of spikes from electric heating are much bigger than they are with water cooling. Water cooling, at least the water that's flowing through the cooling lines is very, very constant. There's very little fluctuation in the temperature in the water flow. So really, only any gradients you're going to have are just going to be from essentially the heat transfer patterns that show up in the steel itself.
Mhm.
With electric heating, this is very much a pulsing problem. Think your stove top. You see it turn on for a little bit, turn off
Mhm.
for a little bit, turn on for a little bit, turn off for a little bit. And there's a thermocouple measuring the temperature at a specific location, and it's feeding that information back to a controller, which is saying pulse on, pulse off, pulse on, pulse off, trying to maintain a set point.
Yep.
So we're doing the same thing here. We intentionally put those heating rods a little ways away from our cavity because we don't want that spiky fluctuation close to our cavity. And then we do another thing. We make the plate that those heater rods are in. So there's a one for the A half of the tool and one down here for the B half of the tool.
Mhm.
We make these plates out of a copper alloy
Wow.
with a really, really high heat transfer rate compared to the steel that is everywhere else. So
Mm.
what effectively happens is we pulse on, and that heat energy quickly, pretty evenly spreads through the copper really fast, much faster than it's conducting down into the next plate below. So we
Mhm.
get pretty quickly an even distribution of heat through the whole plate here, and then we have a pretty even conduction up and down from each of those plates. So
Hmm.
that helps us keep it consistent, and that helps us kind of smooth out the spikes we get from that pulsing effect. Um, from there, the other tool we have at our disposal. So the disadvantage of that is there's a time delay from the time
Mhm.
you pulse, from the time that an energy actually makes it down to the cavity. You've got some time that's elapsed uh, on a significant time scale to a cycle time you might be trying to achieve of maybe 15-20 seconds, maybe more on a bigger part.
Yep.
Um, so we have another thing that we're working with to play with that. Um, the and this is really a heat capacity discussion.
Yep.
You'll notice how small this part is volume wise, and even the runner here, which is massive compared to the part. We'll talk about that in a little bit, time
Yep.
permitting. Um, the total volume of each shot is quite small. The
Mhm.
total volume of the whole stack of plates that we are quote heat soaking. We're bringing the entire mold all the way up to a constant temperature and then holding it there.
Mm-hmm.
There is so much heat energy just stored in all of these plates. That's what we're really counting on doing the cooling. And if you imagine a whole heat transfer equation, think of all of the sources of heat coming in and all of the sources of heat going out. Coming in is from the heater rods themselves and
Mm-hmm.
then from the shot itself. Those are your ins. Your outs are um, from convection just around the outside areas of the tool and air moving past them, pretty small amount. Radiation is the biggest because this thing's really hot and it's
Mm.
radiating a lot of heat off. And then conduction to the mold platens, which we bring down very low by putting some insulator plates. So these little skinny plates on either end are a fiberglass composite with that are thermally insulating.
Gotcha.
So we're really the most of the work these heater rods are doing is actually battling the heat loss due to radiation is the probably 95% of the equation here.
Hmm.
5% or less is actually balancing out the extra heat that's coming in from the hot melt flow.
Mm-hmm.
So the analogy here is if all of the heat energy that's spread through this entire mold base is a swimming pool, each shot of the peak resin coming in is like pouring a cup of water into that swimming pool.
Mm-hmm.
It's really a pretty insignificant um, piece of the equation. So what ends up happening from that is the mold itself becomes the heat sink and becomes the nice controlled um, cooling method for the resin, and that's where we get good consistent crystallinity performance from, because that as long as we get back to stable in the mold base and the heat capacity or kind of the amount of heat storage that's in those plates by the time the next shot happens, now we're consistent.
Hmm.
And that's what we're after. So this works so long as this shot size remains relatively small compared to the mold base plate and components that it's living in.
Okay.
All right, so
Excellent.
that's our talk on
Yeah.
heat and cooling. Talk on venting a little bit here.
Yeah.
So we can see as we zoom in here, we've got several different parting lines or match lines, places where um, air or gas could go through, but also that pesky flash could sneak into.
Mm-hmm.
So the main one, of course, is these main parting line faces on the slides themselves. Um, the that we can solve essentially by just making sure these are nice and flat and we get good crush between them. So we're actually looking at the half of the tool that doesn't have the vents on them, the other half of the tool, but this does have the vent dump, and that's what this is right here. You see this little hole going to the
Mm-hmm.
back of the slide. That's connected to the vacuum system right there.
Hmm.
That's pulling vacuum at the main parting line vents to vent here. Really, we want to strategically place our vents at end of fill. So, because as our melt flow comes in through this gate, it's going to flow around the sides of these pins, and then it's going to make that first knit back here. And the first potential we have for an air trap or a gas trap is right here, where those two wrap around. We could potentially trap air or gas. So we put a vent right there, get that to the dump, and then pull vacuum out through there. Then the main end of fill for the whole part will be up here, kind of far away from the gate. In theory, this would be the very last corner right here. So similarly, we're venting along the kind of interface between this core pin and the hole that it sits inside. So that's where we have what we call the primary vent here, a vent dump to allow that air and gas to expand and kind of not build up pressure or head, so to speak, as it is flowing through there. And then that can flow all the way back up into here and connect to our vacuum system. We actually have two isolated pieces of this on these vacuum lines, one that goes around here, around the head of the pin,
Hmm.
and we have a separate one that actually goes all the way through. So we actually wire a hole
Hmm.
through the middle of this core pin so we can get venting right to here, because this is another area We want to make sure we get a nice crisp. We don't want to trap air right in these little corners. We want to get good fill right up to get this little chamfer feature, which is probably less than a thousandth of an inch. And at the same time, we don't want to flash at this shutoff. So we're controlling this fit and the crush between these two core pins really precisely, but also making sure we're getting good venting through there by pulling the vacuum.
Interesting.
That is
You
kind of it.
You talked about shrinkage earlier. And go ahead.
Yeah. So shrinkage, of course, molten plastic comes in, and it's in this kind of semi-liquid state. And as it cools, it's going to shrink and its density will increase. That's normal of any plastic and kind of intuitive if you even think about really anything we work with in day to day.
Yeah.
So we have to accommodate for that when we cut a tool, because we're chasing a tolerance in the finished frozen solidified plastic part, maybe plus or minus thousandths, plus or minus 25 micron, sometimes tighter. And we might have, I think peak, for instance, is like a 0.12 to 0.17, 0.18% shrink rate, which doesn't sound like much, but when you only have a 2 thou target window, that's significant. So what we do is intentionally size the cavities bigger by the amount of shrinkage we expect to get. And there's published data. We can also run simulations to get an exact number or range or tighter range for a particular part geometry. This one's really nice because the part is so small. There's really not a whole lot of room for variation on longer parts, bigger parts, thinner wall parts. Essentially, every little bit of flow that the plastic has to travel through, the more pressure is required to get it through there. So you can imagine all the way back here, you have a pressure at your nozzle of your press, which is the only place you typically have to control it from. Unless you have a hot manifold system, you get some controls in there too. But generally, all your pressure is coming from your barrel. And then it's going to take some pressure to get through your sprue. It's going to take some pressure to get through your runner. It's going to take a fair bit of pressure to get through your gate. And then depending on how thin your part is, it's going to take pressure to get through every last inch or fraction of an inch of your part. How much shrinkage you get is impacted by a lot of things, but one of the strongest variables in that is the pressure that a particular little slice of your part sees at the time that it freezes. So what, amongst other things, what we're trying to control is that keeping a constant pressure profile kind of timed to the freezing of the part. We're trying, and ideally we get a constant shrinkage rate. So it could happen, let's talk an extreme. Say we just hit this thing really, really hard, we get to fill and then back off. It'd be a horrible process, but you, in theory, could do that. What might happen is while you're at that really high pressure, you get really good pack out right here, but then you let go and what's in there will still freeze, but now you haven't packed it. And so as it freezes, the stuff that's further down near the gate doesn't pack out as much. So it's less dense, so it shrinks more. And maybe you hit your diameter up here, but you didn't hit it down here because you cut the tool with a constant shrinkage rate.
Yeah.
So those are things we're playing with. We're looking for in simulation. We're looking for if you have big changes in wall section. Let's say this came in here, but then you had this big thick area maybe at the other end.
Yeah.
That could be a problem because that big thick area is going to take more plastic volume to reach the same density, and could maybe sink so bad that it results in shrink so poorly that it results in sink, kind of like dish in of what would otherwise be flat surfaces, or warp. All warp ultimately stems from shrinkage differentials locally throughout the part. So these are all things that we're trying to control for. both most of it up front in the we just even when we're quoting or looking at parts for the first time, we're doing that kind of design for manufacturability or that DFM
Yep.
review, and we're giving advice on, hey, good consistent wall sections, trying to avoid things like going from thin to thick wall sections,
Yeah.
trying to avoid areas that might sink, trying to avoid things that get too thin. We're looking for all of those things, amongst others like draft and
Yeah.
other considerations for good molding practice.
Okay. One last question about the shrinkage. Is that something that the customer will spec? Is that an ASTM standard for certain materials? Like what percentage, I guess, is acceptable typically for peak?
Yeah, so the shrinkage values are typically published by the resin manufacturers, because
Okay.
so they'll actually go have their resin tested, and there's a variety of standardized tests to calculate what the empirical shrinkage values are. They're very geometry dependent for a lot of the reasons we just talked about,
Hmm.
and so they'll typically publish a range. Um,
Okay.
that because it's dependent on test data and those tests are very standardized, many of those test standards are based on kind of bigger parts than what we're working with in micromolding.
Hmm.
So a lot of times we have to take that with a grain of salt. A lot of times we have to take it with uh, a whole salt shaker and
Yeah.
go, we really need to do our own empirical testing and get a body of data behind it, which we have over the years. And so we've pretty reliable understanding, based on real life data, um, with parts just like this, these micro parts, these small wall sections, sub 10 thousandths wall thicknesses, long kind of thickness to length
Mm.
ratios, which are particularly challenging for those pressure drop reasons we talked about. Um, and we put a lot of stock into the empirical data we get. All of that can then be fed back into the simulation databases so that you
Okay.
can leverage that, in predictive analyses.
Okay. Excellent. Thanks for sharing that, the mold design and going through a lot of those in detail. That's awesome. Appreciate that.
Yeah,
Uh,
absolutely.
I know that kind of moving on, a couple other subjects we want to touch on: radiopacity, the ability to view peak molded components under X-ray. And I know that I think peak has the same absorption as soft tissue, so it's invisible. So, what are some of the strategies for radiopacity, being
Yeah.
able to see these components under fluoroscopy?
Yes, the simplest and probably most common from what we've seen is same as you'd see in a lot of other resins, is adding a compound into the resin itself. Barium sulfate is a really popular one.
Okay.
It's um, has a large body of data talking to its biocompatibility and kind of safety to use for a lot of those applications. Obviously, asterisk, talk to your compounder, your resin supplier to confirm that.
Yeah.
Um, but yeah, so that's very common. In lower temp materials, you'd probably also see maybe as commonly using markers or inserts
Hmm.
to achieve the same thing. So we see that really commonly in the catheter space. People using platinum iridium,
Yeah.
things like that. Marker bands insert overmolded into the parts and using those for detection on a radioscope. Um, that's in theory possible as well with peak, though with the high temperature mold, there's obviously a lot more complication to that. Um, just physically getting in lower volume and up to a certain production value, a lot of this stuff is done with kind of manual operators. So they're using hand loads. We use fixtures and things like that to help support that and make that easier. All of those get more complicated when everything's hot,
Hmm.
especially if you got a hand load coming in and out of the tool. Not only someone having to do that and obviously wearing gloves and protection, finger cots and things like that. Um, the we also have to worry about all those cooling and thermal control issues we talked about. So it's if
Yeah.
you got a hand load, a piece of the mold is coming in and out of the tool and not sitting there having its temperature maintained by those heater rods we talked about. In those cases, we'll actually use hot plates at
Okay.
the operator desk to keep the temperature control of just that hand load component for it to go back in and out and make sure it stays at a stable temperature. We often have to add a little bit of cycle time to make sure once it goes back in, it has a moment to kind of stabilize with the temperature of the surrounding material or surrounding mold components as well. So can be done. Has some extra complications.
Mhm.
Some areas where kind of feasibility might get in the way of doing that at certain scales, but yeah, those are
Okay.
the two big options. You got fillers for the material
Yep.
to compound in. You've got inserts.
Speaking of insert or over molding, I know PEEK doesn't have very good surface energy, so it's difficult to bond, certainly, and you can't co-extrude it really. And I think maybe a two-shot or a two-component mold is difficult. So how do you, if there applications where you're insert molding over maybe a metal component or some other that are there's some tricks to the trade, so to speak there?
Yeah, so a few different things we see is like you just mentioned, folks overmolding over, say, a metal insert or
Mm,
something like that. Um, that's often more approachable because oftentimes they're fully encapsulated, or you have other mechanical means to trap that type of component. Which, to what you alluded to, yeah, kind of chemically uh,
mm,
or otherwise, bonding PEEK doesn't play real nice for
yeah.
a number of reasons. So mechanical bonding is going to be your best bet in a lot of cases.
Okay.
Um, Similar to if you talk about overmolding of really any materials, the more similar the materials are to each other, typically the
Yeah.
better. In the catheter space, overmolding of different diameters of PBACs we do all the time and are really
Yeah.
familiar with that.
Hmm.
Um, Kind of the biggest one is a bit intuitive of one of the best bonds is when you can actually melt the materials, remelt and have them flow into each other and then resolidify. And that works great when they have similar melt temperatures.
Yes.
Um, if you're trying to overflow, another common overmolding situation we see is, hey, I've got this really strong. I picked PEEK because it's a metal substitute in this situation, but I need a soft tip. I need
Yeah.
and so you want to overmold like a TPU or something like that over the top of a PEEK part. Great idea, can be done. Needs to rely on those mechanical features to do it because that TPU, let's
Yeah.
say, its melt temp is not anywhere remotely close. The
Right.
PEEK is not going to melt at all. You're not going to get remelt at any processing temperature the TPU can handle. Um, and that goes for most thermoplastics.
Yeah.
Um, so yeah, I think that's the
Okay.
gist of it. Stick to those mechanical bonding methods wherever possible.
Gotcha. Excellent. Well, once again, Brett, you've done a great job, and it's been so interesting and informative. And I think the last time we did a podcast, I think I said that we'll have to get you back on again, and I'm going to have to get you on for a third time. We'll have to think about something interesting to talk about, but we'll deal with that later. But thanks so much. Great conversation.
Absolutely. Thanks again for having me. Looking forward to coming on again.
All right.